Alright, welcome back to the final review. This is our last lecture of the class, guys. We made it. So let's pick up with counting. These are more recent things, so hopefully they're more fresh in our brains. Let's talk about the product and sum rules. So the product rule, it's like, alright, if there are A ways of doing one thing and B ways of doing another thing, then there are A times B ways of doing both. So like, here's A, I have 2 ways of doing A, here's B, I have 3 ways of doing B. If I want to do both, I can do this one and this one, or this one and this one, or this one and this one, and same for if I do that one too. So it's multiplied. That's the product rule. There's 6 ways to perform an action of A and an action of B. Product rule. And then the sum rule is if there are A ways of doing one thing and B ways of doing another thing, you can't do both at the same time and they don't overlap, then there are A plus B ways to choose something to do. So for example, if I could do stuff from set A or stuff from set B, not sure which, but I need to decide, I have 5 things I could possibly do. Yeah? So pretty obvious stuff, but we have to put it in math so that we can do fancier things based on these rules, like permutations. So permutations are how many ways can we order the elements of a set? At the end of the day, that's what it really means, right? So I have the set 1, 2, 3, 4 with 4 things in it. What are all the different permutations of these elements of this set? So when there is no duplicates, this is how you do it. So, all right, you could choose 1, 2, 3, 4 in that order, and that's why we have tuples here, because the order matters now for permutations. We could do 1, 2, 4, 3. We could do 1, 3, 2, 4. We could do 1, 3, 4, 2. ... In total, there are 4 factorial ways to permute n elements, right? To permute 4 elements. N factorial ways to permute n elements. Yes? So that's just it comes out of the product rule pretty easily. And we also have fancier permutations, PNR, that counts all the R-sized tuples, all the permute R elements out of n of the elements. Okay, so for example, we could ask for, how do we permute from 4 elements, just 3 of those things? What are all the permutations of 3 elements out of a 4-element set? And so that's looking for things like this. All right, let's take out 3 things only. So 1, 2, 3, that's a possible permutation. 1, 2, 4, possible permutation. You choose from every element, but you can only pick 3. 1, 3, 2, 1, 4, 2. And so this is going to be, well, for the first thing you have 4 elements to pick from. For the second thing you have 3 elements to pick from. For the third thing you have 2 elements to pick from. And so 4 times 3 times 2 is the answer. That's how many different ways you could permute 3 things out of a set of 4 things. Okay, so that's permutations. There's also combinations. Let me remember to say ... there. Combinations is not the order. The order doesn't matter. We just care about what we're picking out. How many different ways are there to pick out some things, make some subsets out of a certain set. Okay, so for example, here's a set S, 1, 2, 3, 4 again. We want to count, for example, all the ways that we could make subsets of size 2. Like how many subsets of size 2 out of S are there? Well, there's 1, 2. Remember that 2, 1 is the set 1, 2, so you don't have duplicates. You can have 1, 3. You could have 1, 4. You can have 2, 3 next. There is no 2, 1. You don't want to double count because that's already been said. 1, 2. See that? So combinations count subsets, keeping track of the idea that you don't have duplicates, order doesn't matter for subsets, and so that gives you this CNR relationship. That is more commonly written like this. That's the choose notation. So n choose r. How many ways are there to choose r things from a size n set? And so the formula is this, PNR over r factorial. So it is defined in terms of permutations. It's just because the order doesn't matter, we divide by how many times we overcounted the same thing. Because we would count the 2, 1 and the 1, 2 separately. We gotta divide away that idea, and so that simplifies to this expression. Okay, so it's always I want to choose r things from a size n set. So this is the size of the original set. And this is the size of the subset that you're trying to make. All right, so that's that. And so for example, the number of subsets of size 2 out of a size 4 set is going to be 4 choose 2, which is 4 factorial over r factorial times n minus r factorial. There's a lot going on there. But you can also do it this way. What's p of nr? That's going to be 4 times 3. Choose 2 things out of a size 4 set, and then over 2 factorial, so that's 2 times 1. So that's going to be 12 different ways, or 12 divided by 2, so 6 different ways. Okay? And hopefully that is correct. We will see. But that is morally correct if I did the math wrong. So that's how you do combinations. We also talked about permutating things, or permuting things, when you have repetitions. So that involves the idea of a multiset, where order still doesn't matter, but you can have more of one thing. You can keep a bunch of ones together, and all those ones are separate. So our standard example for that we learned was word scrambling. So like, how many ways are there to scramble all the letters of like Beyonce or something? And the game was always, there are duplicates, right? You have E's. The game was always, think of your scrambled word as just a bunch of blanks at the start. Numbered. And so now it's a question of choosing which of these numbers to place your letters on. So for the E's, it's like, all right, pick 2 of these numbers, choose 2 numbers, because the order doesn't matter, to put the E's, and then everything else that does not have duplicates, you just place using your normal permutation rules. So there's a factorial involved there, but for the duplicates, there is some choosing going on. There's some combinations going on. So definitely go back to the book for the fancy formula there. But it's going to expand to the book or the previous slides. It's going to expand to, all right, I have 7 places to put things. I need to place the E's. There's 2 of those. So pick the indices for the E's. Order doesn't matter. And then I need 5 more letters, right? So I have 5 factorial more ways I could arrange the 5 remaining letters for the remaining indices that I have not yet filled. All right? So that is counting stuff, permutations with repetitions. And then there's also this idea of counting multisets, so picking 7 dogs from 5 different types of dogs. How do we do that? Well, again, this is about multisets, so I can pick all 5 from the same type. I'm making a set that looks kind of like this. It can have 1, 2, 2, 2, 3, 3. This is, in multiset land, not equal to the multiset 1, 2, 3. In set land it is, but this is a multiset. We care about duplicates now, just not the order. So the number of ways to select n objects from a set of m varieties is this. So, for example, if I had 7 dogs in 5 types, it would be, well, 7 plus 5 minus 1, choose 5 minus 1. And the reason for this is because you're trying to calculate all the binary strings of a certain form. This is how we can make binary strings out of this game that we're playing here. So the number of dogs, the dogs that you pick, those will be 1s in our binary string, and then the types, we'll separate the types by 0s. So if I have, I want 3 dogs of the first variety, I put 1, 1, 1, and then I'm ready to pick dogs from the second variety, I put a 0. And so we can translate this into counting binary strings. That is our trick. And maybe I want 2 dogs of the second variety. Then I'm ready to pick from the third one, so I put a 0. And then I want 1 dog from the third variety, and ready for the fourth, put a 0. 1 dog from the 4th variety, ready for the 5th variety, and I've actually ran out of dogs to pick. 1, 2, 3, 4, 5, 6, 7, so I can't put any more 1s over here. And so really, the reason this formula works is because you're trying to pick, like, the smaller thing. You're trying to pick all the spots that you'll place these 0s. And then the size of your string is the number of 0s plus the number of 1s. There's always m minus 1 zeros because you just want to separate things. You don't need a last one to separate. I hope that makes sense. Hopefully that's coming back to you. But we translate this problem into a counting all the ways we could make a special kind of binary string problem. Okay? Now let's keep going to binomial coefficients. Another way of counting things. It has to do with essentially combinations and permutations again. So let's talk about this. So the binomial coefficient of, so we're expanding this fancy formula, and we want, what is the coefficient associated with a to the k times b to the n minus k? We know because it's to the n, you're going to have this term where those exponents sum to n in some form, okay? And the binomial theorem says that that coefficient is, oh, it's a combination problem. Interesting. Interesting, interesting, interesting. And so that's what happens there. So a plus b cubed, for example, that's going to be, think about it this way. It's got, well, you can pick all a's, you can have AAB, you can have ABA, you can have a lot of stuff in between, you can have BBB. It's just all the different ways you can have these, but these terms are the same, right? You're going to have some terms that all are the same, like the order doesn't matter for multiplication, right? There's some b's, there's some a's, they all align. Those are equal to each other. And so we have several of those. And how many do we have? It's n choose k. It's also equal to n choose n minus k. It's a kind of like a palindrome, the way that this works. So let's see here. For example, let's say how many a squared b to the 1 terms do we have? Because that's what this is. A squared b to the 1, a squared b to the 1. How many are there? Well, it's going to be n choose k. So apparently n is 3. What is k? It's the thing associated with the first number, so 2. It's going to be, whatever goes here is going to be 3 choose 2, which is going to be permute 2 things out of 3 things. So that's 3 times 2 ways to do it, over all the ways that you could have rearranged them, because the order doesn't matter. So 2 factorial, so over 2. And so the answer here is 3. There are 3 a squared b to the 1 terms. And this is also equal to n choose 1 as well. It's a palindrome. And you can also notice this from the Pascal's triangle. 1, 2, 1. We had, I think it was 1, 3, 3, 1 kind of going on here. I think it's this one that we have to pick from. So we could either say that, I think it was this 3. This is the 3 that we're picking out. That's that term, a squared b to the 1. Or it actually might be this one. I can't remember. It's one of those two, but it is, it's a palindrome. It goes in both ways. Okay? So that is binomial coefficients. Remember that if it looks like this, like 5a plus, or 5a minus 7b to the 3rd, you also have to worry about these coefficients. And also remember there's a negative here. So keep in mind that this is not the full story. Go back to the slides for that full story. Okay, let's talk about generation now. So this is part of your last lab, right? So generating permutations and combinations in lexicographic order. So that is a mouthful. And the fancy algorithms are also a mouthful. But I'm going to try and teach you how to run these algorithms in your mind without having to like figure out all these little individual pieces of them, because there's a lot to remember. It's like, what is next perm really doing? Oh gosh, I have to find indices and swap them. What's really happening? Here's what I want you to think about when you're doing the test. To program it, you need all these indices. When you're doing the test, here is how you can think about it. Next perm, for example, like, let's do that one. So let's say we want to permute all of the elements of the set 1, 2, 3, 4. And so the very first one, the very first permutation we output, right, is going to be just the numbers in order. So the first permutation we output is 1, 2, 3, 4. And then we have to call next perm with this one to calculate the next permutation in lexicographic order. So it's got to find some things that hold, where some conditions hold. We've got to worry about all this stuff. And here's how I want you to think about what next perm is really doing. What it's trying to do is rearrange. Can I rearrange the last two? Let's just pick out these last two numbers of the previous permutation. Can I rearrange just those two and make a greater tuple? I guess a subtuple you can think of. Can I rearrange 3, 4 and make something bigger? Yes, I could have made 4, 3. So the next permutation is going to be 1, 2, 4, 3. See that? And then you do it again. Next perm is, can I rearrange the last two numbers and make a greater subtuple? I can't do anything bigger than 4, 3. That's already as big as possible. So if that's not true, try the last 3 numbers. Can you rearrange these to make a bigger tuple? Yes, and remember to make the next bigger tuple. Don't make anything bigger than that. You want the smallest bigger tuple. So what's the smallest bigger tuple of 2, 4, 3? I believe that it's going to be 3 first, right? Because we've already done all the 2's. We've exhausted our 2's. So it's going to be 3 and then 2, 4. So 1, 3, 2, 4. Do you see how that's the next bigger tuple from this one? That's what next perm is really doing. All right, then we have 1. Then we have 2, 4. Can I make, let's always go back to this one. Can I rearrange the last 2 only and make the next bigger one? Yeah, I can do 4, 2. So 1, 3, 4, 2 is the next tuple in order. All right, look at these. Can I make something bigger here? No. Can I make something bigger here? Yes, I totally can. I can put I can put 4 first. So I could be 1, 4, 2, 3. You see that? That's how you do it. 1, 4, 2, 3, and then you look at these again. What's the next one? Can I rearrange just these two and make a bigger subtuple? Yeah, I can make 3, 2. 1, 4, 3, 2. All right? Can't rearrange these. Oh, darn. I can't even rearrange these. So now I need to try the last 4 numbers. I gotta go even bigger. So it's always these 2. Oh no, these 2 aren't big enough. I gotta go these ones. These 2, rearrange. Now it's gotta be all these, rearrange. Now it's gotta be these 2, and now it's rearrange all 4. Oh darn. So the next bigger one is gonna be 2, 1, 3, 4. It's all gonna be in order. It's the smallest bigger tuple, okay? And that's where I want to stop for my example. That's what's happening. That's what this kind of reverse order is really doing. It's making the smallest bigger tuple, okay? And so that's how I want you to think about it on a test for next perm. And then let's talk about next subset as well. Let's generate all of the, because it's always, what's the size of subset as well, given your initial set. Same with that one. Let's say that we want to calculate all the 3 subsets, the subsets of size 3 of 1, 2, 3, 4 again. Okay, so the very first subset it creates is going to be 1, 2, all the way to R, which is 3 for us. So the first subset in lexicographic order is 1, 2, 3. Okay? And then we call off this to next subset. We do some fancy stuff. What's the next subset given what I need? Okay? So what next subset is doing is this. Find the rightmost element of your previous thing that could be bigger. You can choose from 1, 2, 3, and 4, right? So start here. Could this number be bigger? The answer is yes. If so, increase it. And then set everybody after it to 1 plus the element that came before it. All right, there is nothing after the 3, so we're good here. We can just make 1, 2, 4. That's the next in order subset. You see that? This will eventually come naturally. These should make sense if you try enough examples. Okay? And then, again, we look at the rightmost one. Let me keep my arrows, though. I can increment that one. What about this one? Can I increment that one? No, I can't make anything bigger than 4. That means, okay, let's try this one. I can increment that to a 3. Sure. So the next one is 1, 3, and then set everybody after it to 1 plus the previous element. So the next element comes after this, better be 1 plus the previous, so it's 4. That's the next subset. Okay? And then we try again. From the rightmost element, could this one be bigger? No. Could this one be bigger? No, because we're already using the 4. Could this one be bigger? Yes. So the next one is 2, 3, 4. 2, and then the thing that comes after the 2 again, everybody that comes after it is 1 plus the previous. So plus 1 to get to 3, plus 1 to get to the 4. And that is everybody. So I was correct when I did my calculation before, wherever that was. 4 choose 2, it really was. Or no, sorry. I'm doing 4 choose 3 here, but still I trust myself there. So how many 3 subsets of 1, 2, 3, 4 are there? That's 4 choose 3, which is going to be 4 times 3 times 2 over 3 factorial, so 3 times 2. So boop, 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 boop. There are only 4, and that's going to generate them all. Okay, so those are the ways that I want you to think about it in your mind for next perm and next subset. And I hope that will help you even when you're implementing it. Like, at least you know what should have happened. Okay, so that's that. Let's keep on trucking and get into the pigeonhole principle now. So this is a very simple thing, right? It's the idea of, all right, you have some boxes, you have some holes, and you have pigeons. If there are more pigeons than holes, and you know that all the pigeons are in a hole, like I have 3 pigeonholes and 4 pigeons, I know that one of these boxes some pigeons have doubled up on. It must be the case. They could all be in the same box, but in the worst case, there are at least 2 pigeons in one hole. Okay? That's the idea. So we can use that to our advantage for some actually complicated problems. This is all we need for a lot of things, which is cool to think about. So here's my example. A set of 8 numbers. Let's select those 8 numbers from the set 1, 2, all the way through 13 and 14. So we have 14 numbers to choose from. We're picking 8. Show that 2 of the selected numbers must sum to 15. So out of the 8 numbers that you picked, 2 of them must sum to exactly 15. Crazy, huh? So, let's think about it. Let me show you how you use the pigeonhole principle to do this. We need to figure out how many ways are there to select 2 numbers out of this set to sum to 15. First of all, there are 1 and 14, right? You could pick those. You could choose 2 and 13. You could choose 3 and 12. You could choose 4 and 11. You could choose 5 and 10. You can choose 6 and 9. And you could choose 7 and 8. Those are your only options, right? 8 and 7, it's already been included. So how many of these options are there? 1, 2, 3, 4, 5, 6, 7. There are 7 subsets that sum to 15. So with that knowledge, we can actually prove this. There are 7 subsets that sum to 15. But we have used every possible number in each of these subsets. Well, I have used 1 through 14 exactly 1 time. So I'm picking 8 numbers. In the worst case, like I pick 1, 2, 3, 4, 5, 6, 7. Now, to pick an 8th number, in the worst case, I'm going to pick one of these. If I pick 8, oh man, now I have 2 numbers that add to 15. If I pick 11, oh no, now I have 2 numbers that add to 15. No matter what I do, that 8th number is going to put me in one of these subsets. Isn't that wonderful? There are 7 subsets that sum to 15, but we're picking 8 numbers. So those two combine with the idea that each of these subsets, they all range over 1 through 14. That gives us our answer. Okay? 7 subsets, but 8 numbers. That means there's got to be overlap. 2 of those numbers will have belonged to the same subset. That's beautiful. All right. So that is everything that I wanted to say for counting. Let's now get into probability. All right. So, terms about probability. We have experiments. Those are things that result in potential outcomes, like rolling a die, right? You have your potential outcomes of what number comes up, right? So your sample space is all of your outcomes. That's the set of all possible outcomes for a certain experiment. So like you rolling a die, here's your sample space S, and it's going to be 1, 2, 3, 4, 5, 6. Right? So that is sample space, and then events are things that we care about, things that we would like to have happen. And events are subsets of the sample space. So for example, maybe we want one of the lower numbers to show up on our die, so we want to see a 1, 2, or a 3, and we want to calculate that kind of probability. So the event that we care about then is the subset 1, 2, and 3 out of the total sample space. And we also have probability distributions, which give a probability for each potential outcome. So for a fair die, for example, you have 6 possible outcomes. You get a 1, a 2, a 3, a 4, a 5, and a 6. And the probability that you get a 1, or any other number, right, is 1/6, not 1/2. And so a probability distribution takes those outcomes to probabilities. And we would like to see this kind of distribution, for example, for a die. But maybe we have like a loaded die, and so the higher numbers are more likely, something like that. That's another probability distribution. As long as all the possibilities sum to 1, that's fine. But we enjoy uniform distributions because that means that it's very easy to calculate the probability of anything happening. Every outcome has the same probability, so just divide by the number of outcomes, and you're good to go. So for example, the probability of this event happening for a fair die, what's the probability we see 1, 2, or 3? Well, there are 3 outcomes here that we care about, and 6 outcomes total, so it's going to be a 1/2 chance. Yeah. So that's terms in a nutshell, and it gets a bit boring to like crunch numbers and talk about die or dice all day long and think of the proper plural. So here's my example that we're going to be going with for the rest of these next couple slides. So here is my example. The probability, let's say that it's hot outside, just in general, is 0.5, depending on, regardless of where you are on the Earth. And here's a conditional probability. So it's the probability that it's hot outside given that you live in Fresno. Remember that this little bar means given. So under the assumption that you live in Fresno, or you know that you live in Fresno, the probability that it is hot outside given you live there is 0.99, which feels like the right answer, doesn't it, most days? So let's also say that the probability just of a human living in Fresno is like the population of Fresno over the population of the Earth, something like that. So here are some probabilities, and let's use that to remember about our conditional probabilities. So what is this? What does it mean to calculate the probability of some event E given that some other event F has happened? All right. What does that mean? That's using the idea that we know that F has happened to give some more information about E itself. It's like we know that F has happened, so it's just the probability that E and F have both happened, their intersection has occurred, over the probability of F. That's the new updated probability. And let me try and draw this. So here's event E. There's a bunch of different ways for event E to happen, but there are only some ways in which event E and F can both take place, right? So here's event F, it shares some things over here, and then there's some other ways to make F happen. And the idea of the probability of E given F is we know that F has occurred, so we know we are here, we're in one of these cases, and the probability of E, once we know we're in F, is this. These ways to make it true for both of them. Probability that E is true given that F is true. So take those cases, divide by the total number of cases. Okay? For just F. So hopefully that graphic makes a bit of sense, and we can use that to calculate things. So just in general, how would we calculate the probability that it is hot outside intersect you live in Fresno? You can actually solve for that, can't you? Because I have given you the probability that it is hot outside given you live in Fresno. So that's 0.99, right? That's equal to, if you unfold this, that's the probability that it's hot and you live in Fresno. or I should draw it like this, probability that it's hot, intersected you live in Fresno, over the probability that you live in Fresno, which are things that I've given you. So just bring this to this side, and you suddenly know the probability of this intersection. So if you're given a conditional probability, you can solve for that intersection as well. So let's see what this is. With these made-up numbers, it's probably something silly, but let's see. So it's going to be 0.99 over this giant thing. So that is 5.3 e to the 5 over 7.7 e to the 9. That many billion people. Oh, sorry, I was supposed to multiply. That's how you bring that thing over to the other side. It's not divide, it's multiply. That looks better. So like 6.8-ish e to the negative 5. Times 10 to the negative 5. So that's a very small probability, apparently, given my made-up things. So that's that. You also have independent events. When events are independent, there are a bunch of different definitions for independence. They're all equivalent, but one way to tell that two things are independent is when the probability of their intersection of them both happening is the probability of one multiplied by the probability of the other. They don't really share any information. There's no use bringing them together when they're really just separate things. So is this true? Is the probability of E intersect F, or this probability, is this equal to the probability of it's hot outside times the probability that you live in Fresno? I do believe that is not true. Let's find out. So is that equal to 0.5 times whatever this is? I have a feeling that's not correct. Yeah, just by looking at it, these are different numbers. And so for my made-up example, these are not independent events. It being hot and you living in Fresno. It's very likely that it's hot. All right, so that's my conditional probability example, and you can go further with that. You can solve for one conditional probability in terms of its flip side using Bayes' rule, and remember how to make that happen. You can also, if you don't have the probability of B itself, we talked about how to use these ideas. If you knew the probability conditionally of B happening without A happening, so A complement, and you also know the probability of A complement, if you have those at your fingertips, then you can also find the probability of B if you don't know that. Okay? So let's use this idea to figure out what is the probability that you live in Fresno given that it's hot outside. So that's the opposite of this. Yeah? So following our formula, we'll just plug in things. So we know right now the probability of it being hot outside given that we live in Fresno. And we'd like to solve for the opposite, the probability that you live in Fresno given that it's hot outside. That's going to be equal to the other way, times the probability of F over the probability of H. So let's try and calculate that. So that's the probability of the first thing, so that's this one, times the probability that you live in Fresno. Oh, sorry, yeah. That was the probability that you live in Fresno. We multiply that first, though, 0.99, that conditional probability, times that, and then we divide it all by the probability that it's hot outside, which we said was 0.5. That was our example. And so this is apparently 0.00013. If we multiply this by 100, we get the percentage. So it's 0.014%. So with my made-up numbers, apparently it's still very unlikely that you live in Fresno, given how many people are on the Earth. Okay? So that was my fun little example there. Let's keep talking about probability with random variables now. So that's just a special variable that can kind of represent what's going to happen. It's like, that Schrodinger's cat experiment kind of thing. Essentially, a random variable is that. If you look at it, it's made a decision, kind of. So a random variable, it's usually capital, x for example, is a function from your sample space to the real number. So for every outcome of your experiment, you assign a number, and the random variable takes on all those values. You can ask for the range. What are all the possible values that your random variable takes on? That has this kind of notation, x of s, where s is like the entire sample space. And so the standard example that your book has is the sum of two spinners. So we spin them. What are the outcomes that we have happen? So just in general, like a random variable is supposed to be something that takes on all the different possible values, but it's randomly. It's like if you print x right now, maybe the answer is 1, and if you print x later, because it's a random variable, maybe it'll say 3. That's the kind of way that I want you to think of a random variable, okay? And then we can define it like this for our spinners. So we have to talk about what in the world is the sample space if we're asking for the sum of two spinners. What goes on? What are the possible ways that we could spin these two spinners, the blue spinner and the red one, okay? So let's say that the sample space is a bunch of tuples, the value of the blue spinner first and the value of the red spinner second. So our sample space is, well, they could both be 1. The blue one could be 1, the red one could be 2, the blue one can be 1, the red one can be 3, and so on and so forth. So we got 2, 1, 2, 2, 2, 3. These are all independent of each other, by the way. Spinning the blue spinner does not affect the outcome of the red spinner, does it? So that's the sample space, 9 values. And let's say we want to know, like our random variable is supposed to keep track of the sum of the two spinners. So what is, instead of x, let's use y. Let's say that our range for our y random variable is going to be, you give it the entire sample space, it's all the possible sums, right? So we could see, if we printed out our random variable y, we could see 2, that's the smallest number, right? 2, you can see 3, you can see 4. There are a bunch of different ways to see 3 and see 4, right? See 4, you could see 5 by this one, for example, and you can see 6 by this biggest one. So those are the possible values for your random variable y, the sum of two spinners. It could be 1 plus 1, which is 2, all the way up to 3 plus 3, which is 6. So 2, 3, 4, 5, 6. And now let us figure out the distribution of this random variable. And so it's all about, well, taking your outcomes, your 2, 3, 4, 5, and 6. This is the easiest way to do it. You count how many ways each of them could occur. So what's the count? How many ways could we get a 2 for a random variable? Well, it's only if they're 1 and 1. There's only one way. How many ways are there to get a 3? There's this way, and then there's this way. So there's 2 ways. How many ways are there to get a 4? Well, there's this one, there's this one, there's this one. There's 3 ways. How many ways to get a 5? 3, 2, and 2, 3. 2 ways. How many ways to get a 6? Just 1 again. All right, and then we can go from that to the probability of seeing a 2, of the random variable being a 2 when we print it out, of the random variable being a 4 when we print it out. There are, remember, 9 possible outcomes. That's the sum of these counts, of course, because they're all separate. And then we could use that to calculate our probability. So this is 1/9. 1/9 chance that our random variable gives back a 2. 2/9 chance that we see 3. 3/9 chance that we see a 4, and so on and so forth. We have 2/9 again and 1/9 again. So that's the probability of seeing those numbers from our random variable. So for example, 4, you can see that with a 1/3 chance, a 1/3 chance. The random variable comes out of 4. That the sum of your two spinners is the number 4. Okay, so it's all about, random variables are all about taking each outcome and assigning them to a number. That's the key. Okay? You can have multiple different outcomes. So the next thing you can do with a random variable is figure out its expected value. Like, what do we expect to see on average over time for the value of our random variable y? Yeah? So let's bring in all this stuff that we were working on here. Boop. And it's not letting me select very well, so let's do it this way. There we go. So we want to find the expectation, and that's written E, and then in brackets, the random variable, E of x, for a random variable called x, for example. And there's a bunch of different ways to do it. Here's the 2 standard ways. For every outcome, you multiply its probability, or its number, by its probability. And it's usually easier to group them like we did here. And so for each value that your random variable could give back, multiply that value by the probability of getting that value. And those are what we calculated here. Like this right here, this is the probability that, for example, this is the probability that our y random variable was equal to 3. That's the value of the 2 spinners. Yeah? So that's kind of what's going on there. And so let's use this way for our 2 spinners. The expectation, the expected value of our y random variable, gosh, where do I want to put this? Let's just put it here. That's equal to, well, each value times its probability. So 1 times 1/9 plus, oh sorry, that's the count. Excuse me. This is the value for the random variable. It's 2 times 1/9, excuse me. Plus 3 times 2/9. Plus 4 times 3/9. Plus 5 times 2/9. I don't know why I want to make a big giant fraction out of this, but that's the way I feel like writing today. So 5 times 2/9 plus 6 times 1/9. There's a 1/9 chance that you'll see a 6. And so this will give us, on average, what we expect to see for our random variable, if you do this out. And I'm not quite sure what it's supposed to be, but my bets are on 4, because that's like kind of like in the middle. So if you do that, that might give you the answer. Okay? So, that is how you can calculate that. And let me, let's just do it out. Why not? Let's see what this should be. I guess let's take a trip into Python. 2 times 1/9 plus 3 times 2/9 plus 4 times 3/9. Okay, cool. So the answer is 4. Apparently, I was right. The expected value that you should see for the sum of those 2 spinners is 4. Nice, on average, over time. So that's kind of cool. You can also solve for this a bit easier if you take advantage of linearity of expectations. So for example, if you have 2 random variables, the expected value of their sum is the expected value of each of them. You can kind of distribute the expected value, the expectation. And also, if you have a constant that you would like to multiply your random variable by, you can just bring that constant outwards. It's just the expected value of x times that c. All right. So for example, the sum of 2 spinners is really it's really 2 times whatever 1 spinner could give you back, as far as random variables go, right? The expected value for the sum of 2 spinners is 2 times the expected value for the sum of a single spinner. Does that make sense? So let's define this. Let's define the random variable z to be the random variable for the number on a single spinner. On 1 spinner. Okay? And then, what is the expected value of z? Well, here's the output of a single spinner, right? It's either 1, 2, or 3. With what probability? Probability. Well, it's a 1/3 chance it's on a 1, 1/3 chance it's on a 2, 1/3 chance it's on a 3. So the expected value of just z by itself, of a single spinner, is, well, 1 times a third plus 2 times a third plus 3 times a third, which I'm pretty sure is going to be 2. So 1 times a third is just a third, plus 2/3, plus 3/3 is just 1, so that is 2.0, so we get 2. And so the sum, the expected value of the sum of 2 spinners is 2 spinners separately, right? So it's the expected value of z plus z, or that's also equal to the expected value of just the number 2 times z, and sorry, let's make our z's like this maybe, just to show that it's supposed to be not the number 2. 2 times z, and we could use this, we can bring them all out. It's either, well, 2 plus 2, or 2 times 2. So that's also another way to get 4, due to linearity of expectations. And so that was a lot less work, wasn't it? And that's why we like these fancy formulas. Okay, so that's the expectation of a random variable. It's like, what do you expect to see on average over time as the output of your random variable? All right, and finally, let's talk about Bernoulli trials. So what is that? It's an experiment where you have just 2 outcomes, and you have decided that one is called success and the other is called failure. All right, so the standard example of a Bernoulli trial is flipping a coin, because you can define heads to be success if you favor heads, and then failure can be tails. That's the idea. And then we'd like to come up with the distribution of all the successes in a sequence of independent Bernoulli trials. So the next trial does not influence the one after it, and the one before it didn't influence the one that comes after it either. So they're all independent. That distribution is called the binomial distribution, okay? As long as they're independent. So we get that the probability that exactly k successes occur in a sequence of n independent trials, so n and k are variables here, with a probability of success p, that's another variable, and a probability of failure q, well, it must be 1 minus p because there's only success and failure, is equal to this. N choose k times the probability that you see exactly k successes, so that, because they're independent, you can multiply, so p to the k, and then you see summing to n, n minus k then, failures, so q to the n minus k. And because of the different ways that you could have made those successes and failures, you have to use, you have to talk about all the different ways that you could have had that happen, all the different combinations of ways that you could come up with k successes and n minus k failures. So for example, if you had, if you're like flipping a coin 3 times and you care about getting exactly 2 heads, there's many different ways to do that. Like maybe the first 2 rolls, or the first 2 flips were the heads, maybe the last 2 flips were the heads, but you also have the heads were surrounded by tails. There's 3 different ways, and so that's where the choosing comes into play. Choose the different ways that you could have arranged these successes. Where did they occur? Okay? So let's come up with this. Let's use the binomial distribution to discover the probability of getting exactly 3 ones after rolling a die 6 times. So that's pretty lucky, right? So we have to define, what does it mean to be a success? Let's define success as getting a 1 on our die. And then failure is everything else. It's seeing a 2, a 3, a 4, a 5, or a 6. Yeah. And then we have to come up with the probability of success p. That's equal to 1/6. And then the probability of failure is the rest, 1 minus a 6th, which is 5/6. And so we want to see, what is the probability of getting exactly 3 ones when you roll a die 6 times? So we saw 3 ones, so we succeeded, right, 3 times. And that also means, because we rolled it 6 times, we failed 3 times as well, so it adds up to 6. And then we wanted to see exactly 3 successes out of 6 trials. So 6 choose 3. That's the different ways of picking which rolling of the die gave you your success. And so this is what we need to calculate. 6 choose 3 is going to be 6 times 5 times 4, that kind of permutation, over 3 factorial, so that's 3 times 2 times 1. And that's times 1/6 to the 3rd power, and that's times 5/6 to the 3rd power. So let's try and calculate that. So we got 6 times 5 times 4 over 3 times 2 times 1, all that, times 1/6 to the third, all that, let's make it cleaner to look at, all that times 5/6 to the third as well. And that appears to be 0.054. So that's actually bigger than I thought it would be. 0.054. And so that's about 5.4% chance of seeing exactly 3 ones when you roll a die 6 times. So it's actually not horrible odds, but it's still quite unlikely. Yeah, like a 1/20th chance that you see that happening. So that is Bernoulli trials in a nutshell, and hopefully the intuition is all coming back to you. That's really what I care about you remembering and taking away from this class, the intuition. I don't care if you memorize the formulas, but I want you to understand why those formulas make sense and how to come up with them again. Okay, so with that brings us to the end of the last set of slides for our very last lecture. So the end. Yay. So we made it to the end of the class. Thank you for putting up with me, and I will see you either in office hours or sometime while you take the final. Remember the time of the final and everything. Don't miss it. And yeah, good luck. Here are some memes to close us out on our very last lecture. I will see you on the day of the final, perhaps.